Hi. So till now we have discussed about the order notation. Now you should be familiar with big O notations of codes, how you should be thinking about big O of problems that you are going to code. When you are writing the pseudo algorithm in your mind, you should be thinking about the big O notation and then put in the values of n and other inputs, whatever there are, into the expression to find out whether that will pass the time limit or not. If that passes the time limit, then you code that idea, or else you don't. Obviously all these steps assume that you have the correct solution idea, then only it will get accepted. But so that you don't get time limit exceeded on your online usage, this should be your strategy. So we have seen a lot of codes till now on how to find the time complexity. Let's go through one more code. Let's say you have an array which has size n, and then you are given this code that you have an answer variable, you have an I variable, while I is less than n, while I is less than n, and AR of I is not equal to Vi plus plus I is less than n. A weird looking code, right? So think about this problem for a while and try to think about what is the time complexity of this code. Okay, so pause the video right here and resume when you would like to see the solution, and or if you have a solution idea. Okay, so I'm assuming that you have thought about the problem for a while now. So if you think about this, the answer really increases over here, I increases here and here and so on, right? So on the first glance it might see that okay, there are two nested whiles, so you might be tempted to tell okay it's order n square, but it's not. Why? See this I variable, this loop runs when I is till I is less than n, right? This loop runs till I is less than n, right? This part runs till I is less than n, right? So everything here runs only if I is less than n, right? And in every execution of this check, I always increases. I increases here, I increases here. If it increases in both of these, it increases in one execution of this. So in every execution of this while, every execution of this while, every execution of this if, this I definitely increases, right? And I can go only up to n. So there is simply I variable that keeps on going forward one by one, and you would be doing an order one work over here. So this is order one, right? This is order one, but you don't know how many times this will run and this will run, right? But the total number of times this runs plus this runs is order n. Why? Because this will keep on increasing and this will also keep on increasing, and the maximum number of increase that you can have is order n, right? Because there is an n sized array and this runs only till I is less than n, and you do I plus plus in both of them for sure, so it has to increase by 1. In fact, if you think about this code for a while, this is nothing but a linear count. So you have an array, so for you start from 0, while it's not equal to some value v, keep on increasing, and then if it's less than n, that means that value is v, exactly v, then you count the v and then increase I. So you're basically counting the number of times, count number of times v, count number of v. That's what this code is doing. And in fact this is just like going a linear scan on the array and you are counting the number of v's. So this is order n, and the idea is that let's say this loop runs b1 number of times, then in the next iteration it runs b2 number of times, then b3 number of times. We know that b1 plus b2 plus b3 is bound to be less than equal to n, because the total number of times I plus plus can happen is only n, right? So even though if one of these whiles is order 1, one of them can be order n, right? So even if this one of them is order 1, some of them can be order n, but we know that this constraint must follow. So even if on worst case one of them can be order n, the sum of these across all whiles will be order n also. So you cannot do like order n for this loop, this while loop, and then this while loop can also go for n times, so n square. It's not like that. It's rather the total number of instruction runs over here summed across all these while loops is order n. So this is order n in total, not order n square. And this idea is called amortization. So this is just a fancy name, nothing else. It's just simple logic that, like, if you're counting the total number of times the instruction run is order n, because sum of the runs of these whiles across all bigger whiles is actually order n only. So these two while collapse together in only order n rather than order n square. Okay. So don't directly judge by seeing nesting loops, because if they are independent, okay, they will be multiplication, but if they are quite interdependent with each other, you should think about like how many total number of times some instruction is getting executed. Okay. So with that said, I think let's move to the memory complexity part. So till now we have been talking about time complexity a lot. What is memory complexity? So similar to time complexity, you need to have memory in your code, right? Your code, if you remember, in C++, when you are executing codes, there is a memory representation of C++ that you have some, you have the text of the code, then you have static or global stuff over here, like global variables. So all those global variables are defined in a separate space, memory space, global. Okay. And then there is a heap and there is a stack. Okay, this is used in recursion stacks and stuff. Like local variables are stored over here, and local variables of recursion are stored over here, and general variables that you define are uh, stored in heap. And heap grows upward, stack grows downward, right? Something like this a memory representation works, right? So there is a, as you can see, there is a memory requirement for the program to run, right? So the exact number of bits is the notion that we would go about when we are talking about memory complexity. Again, we don't want to count exact number of bits because that will become difficult. So again, we will use the order notation. So suppose you define an array of say n cross n, okay? So there are n square number of cells, right? And each cell, you know, might take, if you define it as int, it might take 4 bytes or 2 bytes based on the version, but it takes 4 bytes now. So as you know that even if you have 4 bytes per cell, 4 is a constant, right? So that doesn't affect our time complexity. So you have total n square number of cells, so the memory complexity will be order n square. Okay. Okay. So similarly in the in a execution, if you see the total number of variables that are being created, you can tell out the number of variables out there, and just the number of variables can be your memory complexity. Okay. So in general, if you're coding some problem, you can define an integer array ARR of 10 to the power 8 in a global scope. Okay. So this is the limit, to be precise. Like, don't go beyond this. 10 to the power 8 is possible. Be safe with 5 into 10 to the power 7 again. So when you are implementing things with mostly the setups are 256 MBs in most of the online judges, but still when you are coding up the solutions, don't go beyond 5 into 10 to the power 7 in memory as well. So you remember, right, how we calculate? Just find the n value, maximum worst case n value, put them in this expression n square. So since the expression is n square, put in n square and find out these values over here, and check that if that is less than equal to this. Okay. So if that's less than equal to this, then you are good to go. Okay. So it's almost similar to time complexity, but now you are counting the memory that is consumed the by the code. Okay. Now let's look at one more problem. Let's say you have some f of n. So let's say you try to calculate the number of instructions of a program. Okay, so you are calculating the time complexity, and you get something like 2 to the power n plus log n plus n squared plus let's say n to the power n. Okay, something like this. You get something like plus some constant and stuff. Okay, so if you have something like this, So everything is happening, like there are sequential executions of algorithms and each of them takes something like this, so you get total complexity like this. So it's something like this. Now in general, when the classes of functions are different, like this is 2 to the power n exponentials, n to the power n is a different class, log n is a different class. When you're writing order notation, you try to write the one that is worst. So which one do you think is the worst in all of this? By worst, I mean to say which will take the worst amount of time, highest amount of time for a given n, as n approaches infinity. N to the power n, right? N to the power n is a very fast growing function. So you should be writing this as order n to the power n, because everything else is less than equal to n to the power n, right? So as in polynomials, we were removing the lower order terms because they were not significant compared to the highest order as we go towards infinity. Similarly, over when we have their different classes of functions in the total complexity, we remove those terms which are less in value as we tend toward infinity, like difference gets start increasing, right? So n to the power n is a really powerful function, and it grows drastically as you go towards infinity. So everything else will be overpowered by this n to the power n, right? So now let's talk about the concept of problems that are called NP hard. What is this NP hard that people talk about? Like, are these like some NP not possible hard or something like this? Okay, okay. So what is this NP hard that we're talking about? So for some problems, we do not yet know if there is an algorithm whose time complexity is bounded by a polynomial. So one particular class of these are called NP complete problems. So they have a nice property that all of them are reducible to one another. So if you solve one NP hard problem in polynomial time, everything else will be solved in a polynomial time as well. Okay, so this is a property of NP hard problems. Okay, and these are not solved. These are not solved. These are yet not proved to be solvable in polynomial time. Okay, so some examples of this would be traveling salesman problem. There are very standard examples of these, finding cliques in graphs and stuff like this. But there are some problems which you cannot find complexity of order uh, n to the power c, something like a polynomial, right? And if you can find, then bingo, you have a paper on your name and like a very good prize as well. I think there is a good prize if you solve NP hard, if you disprove this conjecture that p is equal to NP, or like if you even prove that they are not equal to, that's also something called p is called polynomial problems that are solvable by in polynomial time, and p is not that are not solvable in polynomial time. Okay. Okay. So these are classes of problems. So if you can show any relation between them, then I think you have a big prize with you, but that's pretty difficult. So there are some problems which for which you won't be able to find out complexity of something like n to the power c. So it sometimes help to know which problems are NP hard so that you don't waste your time thinking about some optimal solution, because if someone would have found it by now, it would have been there in a research paper or it would have been present in some paper and you would have known about that standard problem. But if you know that it's NP hard, that means nobody has yet found it. So there is a very slim chance that you, I think there is a no chance that you would be able to find a solution to that. Okay, so you should know that it's not always possible to decrease time complexity to any extent. Like there is some lower bounds on solving ideas of problems. Okay? And there is this NP hard that you cannot solve in polynomial time. Like you will need some brute force algorithm that will take some 2 to the power n or even n to the power n. Okay, something like this, something like this complexity are like the solution ideas that solve NP hard problems. Okay. So that's all for this video. See you in the next one.